The material which we have just covered at the end of the last lecture is of an importance such that I want to briefly review it as we go on. This is our beginning of the main part of our Lie algebra course. And to quickly review this, we have defined a Lie algebra as a linear vector space with a basis for that linear vector space that's finite dimensional. It may have n different basis elements, and the commutator or bracket that is defined for that space is an antisymmetrical form, and one has closure, so that the bracket of two elements is again a linear combination using summation convention here, Cij. These Cij are the structure constants. The Lie group is obtained by taking all of the forms e to the lambda dot L for the entire Lie algebra elements L, and that generates, by the normal expression of exponentiation, all of the elements of the group. Now, the core aspects of the Lie algebra itself are the existence of the structure constants that obey this equation right here, that are antisymmetric in I and J, that also obey the Jacobi identity. You might say that the lambda dot L generates a transformation that's continuous from lambda equal to 0, or actually lambda equals minus infinity to lambda equals to plus infinity for this Lie group element here. So this is the algebra. This whole thing is the group. The core equations that I quickly review here are the fact that we can take that Lie algebra and cast it into a different form. This different form has a maximum number of commuting operators called the Cartan subalgebra, which we're going to rename as H. The H1 up to HL are the maximum number of linear combinations of basis elements in the algebra that all commute with one another. So Hi, Hj vanishes. And that also means that there's no combination of the rest of the elements that will commute with all of the h's that's linear. The rest of the elements, we can form linear combinations of those to form two types of objects, an E plus alpha and an E minus alpha. These always occur in pairs, such that the commutator of the h with the e's is a set of constants Ri plus or minus alpha with that same alpha again. Now this particular combination, h with e is something times the e back again, always means that e is a raising operator for the eigenvalues of the h's, as we will see later. The commutator of the e plus with the e minus alpha always gives you an h with a vector Ri. Here the vector is with a superscript rather than a subscript. And the E alpha with an E beta always gives you something with an E alpha plus E beta in alpha beta. Now these have the properties that the Ri lower is the metric tensor Gij times the Rj upper for the same alpha, where the metric tensor is defined as a double contraction of the structure constants. This will therefore equal to this expression here, which equals this expression here, which is the normalization of this system. The h's are the maximum Cartan subalgebra. The e plus or minus is raise and lower those eigenvalues. This is called the Cartan decomposition of the algebra. You'll recall also last time we talked about the order of a Lie algebra as the number of basis elements. So if the algebra has 7 elements in terms of which all of the rest can be expressed that are linearly independent, the order would be 7. The rank is the number of maximum commuting objects. So obviously the rank is, symbol is not clear here. The rank is less than or equal to the order of the algebra. Now, one of the main things that we learned in that last lecture was that you can have nonlinear functions of the L's that do commute with everything, and these are called the Casimir operators. There are a whole set of those. And these Casimir operators are such that the C mu's, for mu equal to 1, 2, 3, and so forth, commute with every one of the L's. A perfect example is J squared with angular momenta. You can also have a set of D operators, which are nonlinear objects. They don't commute with all of them, but they commute with all of the H's. We will later see that these are actually Casimir operators for subgroups of the algebra. So all in all, C's commute with C's, C's commute with D's, C's commute with L's, D's commute with H's, D's commute with D's, and that's a requirement, of course, and the H's commute with the H's. So we can label all of the representation space with a set of C's, a set of D's, and a set of H's as their corresponding capital letter Lie algebra components all commute with one another. That brings us to the discussion that we want to have today. What are the simple Lie algebras? Well, the semi-simple Lie algebras are the ones for which the metric tensor is non-singular, Gij, that we just introduced. So let's go over a few important concepts and definitions. A subalgebra of a Lie algebra is a subset that in itself is a Lie algebra. Okay, that's kind of obvious. An invariant subalgebra is a subalgebra such that if we take the commutator of any element in the subalgebra with any element in the larger algebra, the result is always in the subalgebra. An algebra is abelian if all the structure constants vanish. But in other words, everything, the bracket vanishes between all two elements. An example of that would be x, y, and z for position in quantum mechanics. All of three of those operators commute. A semi-simple Lie algebra is one that has no abelian invariant subalgebra. In other words, of these invariant subalgebras, there are none that are abelian. A simple Lie algebra is one that has no invariant subalgebra at all. We now need to go through the list of simple Lie algebras. These are in 4 series. Each of these series is an infinite number of algebras of a given category. They're normally categorized as the A's, B's, C's, and D's. Then there are 5 exceptional algebras: G2, F4, E6, E7, and E8. We will be looking at both the order of these algebras and really what these algebras do, how they can be physically interpreted. And these algebras that we have just listed are, according to Cartan and Lie, the entire number of solutions to the structure constants being antisymmetric and obeying the Jacobi identity. The first of these, AL, where L is 1, 2, 3, all the way up to infinity, is a whole sequence of Lie algebras that are the same as the simple unitary group in L plus 1 dimensions. That means that L1 corresponds to SU2. And the order of the algebra is given by, and remember that the order of the algebra are the number of elements that we have, the number of basis elements, and the rank of the algebra is given by the number of commuting elements. So the order is given by L squared plus 2L, and these are, we can see, the simple unitary matrices in 2 dimensions. For L2, we would have SU3, and so forth. Now, these are traceless, and when we say simple, we really mean that we have taken the diagonal or the trace of these elements away, or that we've taken basically an overall factor out of these elements that commutes with everything, which is the element 1, 1, 1, 1, and so forth along the diagonal. The second set of algebras are called the BLs, and that starts with 2, 3, 4 up to infinity. They have an order 2L squared plus L, and they are isomorphic to the O2L plus 1 orthogonal group in odd dimensions. We can see that it's odd number of dimensions. For example, if we take L is equal to 2 here, B2, what is B2 going to be? Well, B2 would be 2 times 2 is 4 plus 1 is 5. That would be the orthogonal group in 5 dimensions. If we were to have an L1, what would that be? L1 would be 2 plus 1, or O3. However, L1 is not listed here because O3, the orthogonal group in 3 dimensions, is isomorphic to SU2. So this B1 here does not appear because it's isomorphic to the SU2 or the A1. So we would be repeating ourselves if we listed it here also. The next set are called the C's, where C starts with 3, 4, and goes to infinity. That has order 2L squared plus L. These are the symplectic transformations. They actually preserve an antisymmetric form, which is left invariant. Next are the DLs, where L is 4, 5, all the way up to infinity. They have order 2L squared minus L, slightly different from this. And they correspond to the orthogonal group in even dimensions. So we can see that the lowest one of these is L4, and that would be the orthogonal group in 8 dimensions. The exceptional algebras have the following orders: 14, 52, 78, 133, and 248. The ranks of these are 2, 4, 6, 7, and 8, and there are no others. Those are called the exceptional algebras. At this time, let me define 2 concepts that will also be important later on, along with these concepts such as invariant algebra, simple, and semisimple. A nilpotent Lie algebra obeys the following equation. If I take the commutator of any element with any other element, A and B, and then the commutator of that with A, and that with A, and that with A, at some point, if this vanishes for every one for all of the A's and the B's, at some power of this commutation, then we say that the algebra is nilpotent. A perfect example of that is the one that we have in quantum mechanics. Because if we take the commutator of x and p, we get IH bar. Well, IH bar commutes with both x and p, so no matter how we do this, we end up with 0 pretty soon. Compact Lie algebras, or Lie groups, is if the group manifold is closed, then we say it's compact. Otherwise, it's non-compact. It's compact, that is, if every infinite subset contains a sequence which converges to an element that's in the algebra. An example of a non-compact Lie algebra and Lie group is the Lorentz group. And the reason for that is the transformation to the speed of light is not present, yet any speed up to that point. So if we think of we could make a sequence of faster and faster Lorentz transformations all the way up to the limiting point, which would be the transformation of the speed of light, but that is not a valid Lorentz transformation. Therefore, that group is non-compact. To review again why some of those algebras did not appear, let me point out the following. Just some miscellaneous facts. If we think about the rotations in 3 dimensions, that group is both simple and compact. And it is, as I mentioned before, it's the orthogonal group in 3 dimensions, sometimes called R3, the rotations in 3 dimensions. And it is isomorphic to SU2. In other words, the rotations in 3 dimensions, 3 by 3 matrices that are orthogonal, can be put in one-to-one correspondence with the correct commutation rules with the simple unitary transformations in 2 dimensions. The Lorentz group is non-compact, and the Poincare group, therefore, is also non-compact. The Heisenberg group is nilpotent. That is, the sequence of commutators finally always gives 0. The Markov group that we'll talk about later is not semi-simple. There you have the commutator of A and B is A minus B, and one notices that this Markov group, which will play a very important role in what we do toward the end of the course and some of the directions we take, this Markov group, the corresponding algebra for it, has two elements, and this is as you might say as elementary a Lie algebra as one can possibly get. We can't use the word simple because that's technical. Usually, and always for simple Lie algebras, we will need L Casimir operators if the rank of the algebra is L. So when we have a rank 4 algebra, if it's semi-simple, we're guaranteed that we need exactly L Casimir operators to specify the representation space that is irreducible. Now one notes, and we kind of went over this a little bit when we talked about the various algebras, for the semi-simple Lie algebras, B1 was the same as A1, and therefore B1 was not listed. That is, the orthogonal group in 3 dimensions is SU2. It turns out that C2 is the same as B2, and C1 is the same as A1. Now if we go back and review that, that means the symplectic transformations, that is preserving an antisymmetric form of rank 1, was the same as SU2. Of 2, it's the same as the orthogonal group in, let's see, B2 is 5 dimensions. And so that does not appear. So we have the equality between these. Then D begins at 4. D1, it turns out, is abelian. That's the orthogonal group in 2 dimensions. D2 is not simple, and D3 is the same as A3. That's the reason that we do not have D1, D2, and D3, and B1, C1, and C2. After we extensively study a number of these Lorentz algebras and Lorentz groups, we will return to the formal theory of Lie algebras and go through the exhaustive derivation that Lie and Cartan did in their derivation. Let's look at Lie groups generally now. We have an equation where the group is equal to e to some real parameter lambda times L, where L is a member of the Lie algebra. And this is the correspondence, this one-to-one correspondence we have between L and G. And of course, using the parameter lambda, we map out a whole trajectory, G, which is a function of both lambda and of L. Now actually, of course, the lambda could be absorbed into the L and still give us another L that's in that space. It's just convenient to separate out one factor of lambda that we say parametrizes the transformation. We therefore write G of lambda and refer to a specific element of the Lie algebra, which is L, which would be, for example, if we had an n dimensional Lie algebra, lambda 1 L1 plus lambda 2 L2 up to lambda n Ln, where this lambda 1 to lambda n, L1 to Ln, constitutes the basis for this Lie algebra. Now as lambda varies over all of the, say, possibly real elements from minus infinity to plus infinity, we then obtain the identity of the Lie group when lambda is equal to 0. Because when lambda is equal to 0, we get e to the 0, which gives us the identity element 1. And so this is basically why we say that we are, as lambda becomes infinitesimal and we move away from the identity, why we say that the Lie group is mapping out all of the transformations that are infinitesimally near the identity. Precisely because as we move away from lambda is equal to 0 to larger and larger values of lambda, then of course we're moving away from that one element where G was equal to 1. Also, we can easily see that the inverse of any element, e to the lambda L, is e to the minus lambda L. Because since L commutes with L, e to the minus lambda L and e to the lambda L is equal to e to the 0, which is equal to 1. Therefore, it's very easy to see what the inverse is for any one of these elements. Now this will become very important when we talk about especially Markov processes, but in general, we will see that for any element, it's very easy to see what the inverse of that transformation is. It's simply the one with the negative parameter. Furthermore, we can see that the Lie algebra defines an element in the Lie group infinitesimally near to the neighborhood. If we took lambda is equal to epsilon, then we can write e to the epsilon times L as 1 plus epsilon times L, and then ignore higher orders than epsilon, because we would have here infinitesimal squared, infinitesimal cubed terms, and so forth, which, close enough to the identity, can always be ignored. This is an extremely important equation. E to the epsilon times L is 1 plus epsilon times L. And often, in the neighborhood of the identity, we can see how we would imagine a given transformation. How do we do that? Well, we do that in the following way. Like this gives the Lie group over here, this would give the Lie algebra over here. If you had a group like the rotation group, cosine theta, sine theta, minus sine theta, cosine theta as the four elements, one could take and say, how do we find the infinitesimal generator? How do we find the Lie algebra element that corresponds to that? The answer is take theta equal to an infinitesimal. And if you do that, you get a new type of matrix that involves epsilon to the lowest order. You then, of course, write that in the form 1 plus epsilon times some matrix. And then you can separate that matrix out and say, that matrix must be the one that generates the entire finite transformation. That matrix then is the one that lets you study the beginning of that component of the Lie algebra. So you do that for each one of the elements. Maybe you do it for Jx, Jy, and Jz, and you get the three different matrix forms of that, and then form their commutation rules. After you form the commutation rules, you would be establishing the structure constants for the algebra. At that point, you take the structure constants and say, let's forget what our origins were here, take these structure constants and find all realizations of the algebra. Now that process that I just mentioned, find a Lie algebra in a matrix form, discover what the structure constants are, and then erase that and say, I'm starting with these structure constants, find all realizations. You will not only uncover where you just were with those matrices, but you will also uncover other matrices and other realizations of that same set of commutation rules. Thus, by dealing with the Lie algebra, we can get to the essence of every transformation and not deal with the the infinite number of group transformations. For example, e to the theta J3 gives us a rotation by the amount of the angle theta. It allows us to study J3 to represent all the rotations in the plane and not have to study this infinite number of different transformations as represented by the group.